Welcome to Embedded Systems. Today we are introducing Project 2 for the spring 2020 semester. A couple things on the horizon. We have Lab 4 due this Thursday. It's a group lab. And then we're going to be doing a few things simultaneously. We're going to be starting to work on checkpoint 1 for the lab, for the project, due next Tuesday the 16th. And then homework 5, which is due on Thursday, the 18th. And then we have several other due dates for the rest of the semester for checkpoint 2 and a functionality for the project, and we'll get into those in a little bit. And then the competition. We also have an exam on April 28th. So today we're going to be working on Lab 4, finishing that up, and then getting started with Project 2, IR decoding. So what does that entail? You're going to be mounting a small breadboard on the side of your robot, if you haven't already, to use to mount the IR decoder on there. Probably already have one there with a button and maybe an LED or something like that. But the IR receiver module that you're going to use is the one in the LED kit that you bought. And it's shown here on the left. If you had just an IR receiver, which some kits may have that, it's pinned out slightly different from the IR receiver module. They basically invert or transpose the ground and the source voltage. So you got to make sure you hook up power and ground to the right pins, or it's not going to work very well. This picture on the right shows my IR receiver, close up to that, where I hook up the 3 wires to the ground VCC and the output signal going to my Arduino. So, just an introduction to the IR signal before we get into it. Nominally, when it comes in, your signal is going to be nominally high. And it's going to transition low. That's going to tell your Arduino, hey, I'm starting to send you an IR pulse from some sort of TV remote. And you can use whatever remote you want. You can use the one that's in your kit, or you can use a standard TV remote, and that's fine. So on that first down pulse, we get a logic 0 half bit. So that's half the cycle. We have a 0 half bit. And we get a logic 1 half bit as it goes up, it transitions to logic 1, and then for a period of time, it's held high. These are logic 0 and logic 1 half bits. Together, they formulate the start bit, which are typically longer bits than all the others, which we'll see when we look at some of the examples. Then we're going to get a logic 0 half bit. That may be a shorter one, followed by maybe a short logic 1 half bit. This is going to be a 0 bit. A short logic 0 followed by a longer logic 1 is going to be a 1 bit. And you can notice, as you look at this, you can tell the difference between 1s and 0s just by looking at the logic 1 half bits. If it's a short one, that's a 0. If it's a long one, it's a logic 1. Typically, all these logic 0 half bits will be the same length of time, same counts. So we're going to get eventually 32 bits in there, and then we'll get a short logic 0 followed by a long logic 1, which essentially means that it stops. And you may or may not get that last logic 1 to come out in your counts. But we're going to have 32 bits here, and that is going to be the code that tells us what button on the IR remote and what IR remote and TV it's for. It's all encoded into those bits. You're going to answer a few questions, and all this will be on the pre-lab, the checkpoint 1. These first few questions are essentially going back to what you already know about how each of those timer runs, and think about how long it takes to to get the timer to roll over and how long each timer count lasts. And if you wonder, that all depends on how you set it up. That's true. But if you look online, the course page for checkpoint 1, I give you a test INO file. That test INO file specifically tells you, and there's a few lines of code in there, to how to set up your timer. Obviously, you're going to be a divide by 64 prescaler, and then we're going to configure up to output compare so we can get it to reset on or generate an interrupt after 65 milliseconds. You're going to figure out those. You're going to figure out a few other lines of code to reset the timer, and CTC mode with output compare register 1A as the top, and so on and so forth. So answering those questions. You'll also notice, if you read through the handout, you need to be hooking it up to port D pin 2, which in my comments I give you the answer to that question, which is digital pin 2. The project PDF, if you take a look at that, it tells you on your Arduino where to connect that output signal on port D pin 2. And then it tells you what those IR receiver signal looks like. And then we're going to also, for this checkpoint 1, we're going to annotate this waveform diagram, which shows logic 0 and logic 1 half pulses for lines 48 to 51 and 52 to 54. And those are shown right here. You have 48 to 50, and then 52 to 54. These lines of code need to be annotated here on this waveform diagram. I've already given you the first one. 49 is right here. 49. That is when it's being held, so it's looking at that decoder pin. When it's low, it's going to be waiting there until it goes transitions high. So you can probably tell from that it's going to put a value, whatever is in the timer counter for time 0, into whatever sample we are putting it into. And then we reset the counter again, and then it holds it at 1, logic 1, and then puts that timer count value in there for the timer 1. And this, over on the right, shows you an example output from that test code. Once you insert those few lines of code to set up your timer, it's going to run, and it's going to essentially count. It's going to give you out time logic 1 and time logic 0, and I'm not showing you the logic 0 ones because they don't really matter too much, other than there's a few questions that you need to answer. But all the data is in time logic 1. So you can see that first bit coming in is going to be a start bit because it's a lot longer, a lot more counts. And you have a few 1s followed by a few 0s because they're shorter. So long bits, then short bits. Those are 1s and 0s all the way through 32. And then the last one would be our stop bit, which doesn't always catch that stop bit because the interrupt will execute. So, again, when you have this received signal on int 0, logic 0 half bit, logic 1 half bit, the start bit is going to be longer, and you have short bits and long bits designating 1s and 0s. We're only looking at the 1 half pulse until we get a stop bit. We're going to get 32 bits. So, once you hook up your code, once you put in those few lines of code posted online, The comments are in there, write a line of code to do this, to do that. Once that's done, you can run it, put it on the board, upload it, so that it's hooked up to that, your IR decoder is hooked up to that pin. Plug it in, look at our serial port, and it's going to say starting up and then waiting for IR input. As soon as I press a button, it's going to spit out your time logic 1 register and your time logic 0 registers. So time 0 and time 1. You can actually copy all this, copy those lines, and then you can start decoding it, because part of what you're going to have to do is decode your logic 0 and 1/2 pulses. So you're going to find out how long in milliseconds and in counts, hex and decimal, for logic 0 and 1/2 pulse for a start bit, a data 1 bit, a data 0 bit, and a stop bit. The stop bit you're going to have to adjust a little bit to get that one. Adjust the code a little bit. So, you can copy that. A good way to do this, I'm going to show you in a little bit actually how to do that. Another thing, what you're also going to have to do is you're going to have to look at the range of the timer 1 counts to classify them as ones to a 99.99994 blah 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 percent of the pulses. If you look at this standard deviation table on this website, to 4 nines, so 942. So we want to get at least that many of the pulses. So that's essentially, if you look here, is 5 sigma. So that means plus or minus 5 standard deviations. So you can figure out what the range will be for the data 1 logic 1/2 pulses, data 0 logic 0, and the logic 1/2 pulses. So it doesn't matter if you do data 1 logic 0, logic 0/2 pulses are all essentially the same for logic 0 and logic 1. As you can tell, they're all about the same. But what I would suggest to be able to go through and figure out 10 buttons, so you need to figure out 10 different buttons on your remote and the hex code that corresponds to those buttons. That's the last part of this. Best way to do this, and figuring out all those tables and those counts for checkpoint 1, is copy all that code, copy this from the output of the terminal, open up a text box. So I'm going to open up a text document. Just going to say new text document. Test. And I'm going to just copy in all that stuff. You can also go in and you can change the output so it doesn't output the time 1 and time 0 and the index number if you want. I find it's kind of nice to just have it. So you save that. And then you can open Excel. Open up a new workbook. And I'm going to open up that file that I just downloaded. So test.txt. You might have to say open up all files or view all files. I want to delimit it by spaces. So I'm going to go next, and I'm going to use space as my delimiter, so I'm actually, when I select that, notice it puts each of those values in different cells, so I can actually manipulate those. Finish. Once I get them all in, notice it actually puts those values in different cells in here. If I had just pasted it in, it would put it all in one cell, which is fine. You can do that later. just find this was easier for me. You can then, as you go through, you need to make some notes so you know what this is. You know this is a start date. Right, start date. And then a 1 date, right? And so on and so forth. You can convert these to say equals decimal to hex. And put this bit and then the number of places, 4 digits, let's say, and it can convert it to hex values. And then flow down, notice the hex values for all those values here. You can then use Excel to figure out the average for these 1 bits. So let's say you wanted to find the 1/2 bit. Or actually here, let's just find the 0 bits. These are the 0 bits down here. So we're going to find an average of all 0 half bits. Average. And then you can get standard deviation. You can do the same thing. This. Deviation. So this is our standard deviation. So if we wanted to figure out the range for that, then we just add and subtract 5 times this on our range. So we have logic 1s and logic 0. You can actually go through and figure out if you have, say, looking at this value here, you can say if this value is, say, greater than 400, it's a 1, otherwise it's a 0. Right? Go back down. These are your 32 bits. Right here. That's 32. As you can see, 32 rows. This is my binary digits. And if you read them from the top to the bottom, you're going to have E. So 1, 1, 1, 0, 0, 0, 0, 0. So you got an E, a 0, another E, 0, 0, and the last one's 9. So my hex code is for that up button. It's going to be 0x E 0 E 0 0 6 F. That's my 32-bit hex value. You can also go through and you can actually concatenate this if you want. There's pretty. Let's see. I go through and I look through. I can concatenate binary to hex and I can concatenate those bits. But ultimately, this is my hex code. So, that, in a nutshell, is checkpoint 1. We're going to go through, similar to what I have done, we're going to go through and figure out all the buttons for 10 different buttons. You're going to do the range for your data 1, logic 1, data 0, logic 0 and 1 half pulses. Within 5 standard deviations, figure out in milliseconds for your timer counts, as well as your decimal and hex count values. You can calculate the milliseconds. You don't need a logic analyzer to do that, but if you have a logic analyzer, you can run pulse view and get something like this. The signal as it's coming in, this is a Samsung TV remote that I've looked at using that same code. Looked it up, as you see the start pulse, and then you see some logic 1, logic 1, logic 1, then a bunch of zeros, logic 1s, 3 of them. And I use this timing, and I can actually see how long each of those pulses are. It's about 4.5 milliseconds for the logic 0 and logic 1 half pulse for the start bit. And then we have roughly half, 565 microseconds for the logic 0 half pulse, and then the logic 1 is about 1.716 milliseconds. And logic 1 0 half pulse is still around 582. But you don't need this to see it. If you have a logic analyzer and you can use pulse view to actually run it, it's kind of nice. They even have an IR decoder where you can actually decode that into the hex button if you want to learn how to get that to work. But otherwise, you're going to be putting it in Excel, and you're going to be calculating 10 buttons, 10 different buttons, and uploading those to Canvas, as well as all the other requirements for checkpoint 1 by next week. So that covers checkpoint 1. The rest of this you might look at later. The rest of this actually involves the other code that I posted online for checkpoint 2. Post in a project 2 INO and that IR decoder H and CPP file. When you get to running those, this code right here, in a nutshell, describes what's going to be in your main code. So you have a main loop here. What's going to happen in the main loop. Then you also have an ISR for the int vectors. And there's a few things that you're going to have to calculate for your IR decoder. You're going to need average, logic 0 half pulses, min and max, so this is where your range is. I found that about 100 counts on either side, plus or minus, gets you pretty much all of the logic 0s and logic 1s. But you're going to find the range to get you within basically 5 standard deviations, 5 sigma of that. There's also some other pound defines that are going to be used later for the rest of the code. This code is running so that once you decode those button presses, so you pound define some buttons that once you pound define these buttons in here, you have your 10 buttons. There's some other pound defines in that header file that I showed you to convert it to look for high to low transitions or low to high. The main code, that's where you're going to have the decoder setup. enable global interrupts, and then you're going to have this, you're going to basically look at and pull this IR packet flag. All the values that are needed in your IR decoder setup. You're going to set up timer 1, CTC mode with output compare register 1A as your top, just similar to what we've done before, rescaler. But I just noticed as I was looking in here, this is off. Should be a divide by 64 rescaler to get, well, you could use divide by 8 too. I'd set it up in the test file as a divide by 64. You're going to clear that counter, similar to what we did before, or similar to what I did in the test code. Sent in 0 pin as an input, so what you need to do is set that up. You're going to set up a pull-up resistor, enable that interrupt, and enable the falling edge of that interrupt. There's a few global variables. You have a packet data file. We're going to be looking at those logic 1 bits. And we're going to have 34 values in that array. And then you're going to do, in the interrupt, on the falling edge, you're going to do one thing, and on the rising edge, you're going to do another. Right? We only really want to look at the data when it's high. So on that falling edge, that's when you're going to read that, store that count data in the packet data. So you're going to classify it as a 1 or a 0 and shift that into your IR packet. And you're going to read that count register first so you can store that value. Then you're going to disable that interrupt. Enable the other edge, which I have found up fine for that high to low and low to high. Make it kind of easy for you. And then on the rising edge, all we do is clear the timer and change the edge. If what the compare A vector, so if we reach our output compare register count, then we're going to disable the T1 interrupt, clear the IR packet, and save it, set we have a new flag. That's going to only happen when we have this really long stop bit. So once we get that stop bit, and that's the same way it works with this code as well, the test INO file. When it gets that 65 milliseconds, it's going to stop and say, hey, we have a new packet. Set aside new flags for your main code. Once you decode 10 buttons on your TV remote or your Elegoo remote, you should be able to tie that to control your robot, make it move forward, backwards, stop, turn, and some other things, whatever you want to make it do. If you want to take a look at the different logic analyzers, you can. Let's take a look at Pulse View. That is the software that I use when I run it. This shows that test waveform coming in for the button press. And this is with the timing on there as well. If you use the SEC lab, if you're able to get to the campus, you do not have to for this. But you can also look at it there. This is an output in that lab. Make sure, either one, make sure you have enough samples that you're going to receive the signal and accurately display it. The robot competition for this one and A functionality is going to be set up similarly to what we did before. We have a 20-foot wall that we're going to follow, but we're going to go around an obstacle. As you can see by the arrow, when you go around this obstacle, you really only need one obstacle, so you're not in the way. For the competition, we're going to have 4 different checkpoints. So you can read C points, whether you make it all the way through, but for full points on a functionality, you make it all the way through and stay within a foot of the wall. So that summarizes project 2.